Leonardo Pisano, otherwise known as Fibonacci, was born in Pisa, Italy, in 1175. He came from a wealthy family which allowed him to travel, learning many different arithmetic systems through interactions with merchants. Fibonacci numbers were introduced in 1202 in the book Libro Becci, meaning Book of Abacus, written by Fibonacci. They were most notably mentioned in the form of a sequence appropriately named the Fibonacci Sequence. Two 12th century mathematicians were known to influence the demonstration of the sequence, Michael Scotus and Plato. Each term in this sequence is the sum of the two previous terms. The sequence was first observed during a thought experiment about breeding rabbits with certain control methods. Assuming no rabbits die, and the rabbits mature after 1 month, and they reproduce once a month, the rabbits followed the sequence perfectly, therefore placing a great significance on the specific set of numbers.
0, 1, 1, 2, 3, 5, 8, 13, 21, 34, and so on. This is the Fibonacci sequence, and it is certainly one of the most renowned mathematical phenomenon in the world. Intuitively, just by looking at the numbers, you can see that any given number is produced by summing together the two consecutive numbers that came before it. 8, for example, the 7th term in the sequence, is given by summing together the 5th and the 6th terms, which are 3 and 5. This occurs for each term, and so a formula can be derived. Fn equals Fn minus 1 plus Fn minus 2. Using 8, the 7th term, you can see that F7 equals F6 plus F5, which is the same result obtained intuitively in the earlier example. However, this formula does pose an issue as it fails to define F0 and F1, as there is not enough terms before these terms to sum together. To solve this, F0 is defined as 0 and F1 is defined as 1. In fact, these definitions are characteristic of the Fibonacci sequence, and they can be changed to produce other unique sequences. An example of this is the Lucas sequence, which starts at L0 equals 2 and L1 equals 1. There are many interesting mathematical properties of the Fibonacci sequence. However, the most well-known, and perhaps the most exciting, is its relationship with the golden ratio. Take, for example, the numbers 3 and 2. Dividing 3 by 2 will of course give 1.5. If you move up by 1 in the sequence, so that you are now considering the 6th and 5th term, and you divide them in the same way, you will get 1.66 repeater. If you continue in this fashion, such that you take one term in the sequence and divide it by the previous term, you will start to notice the resulting numbers you obtain are approaching a particular value. This value, to 3 decimal places, is 1.618 and is denoted by the Greek letter phi. This can be represented mathematically by following the limit of phi equals Fn on Fn minus 1, as n tends to infinity, is equal to 1.618. This is in fact the golden ratio. It's also called the golden ratio because it seems to appear in nature everywhere, from seashells to galaxies to all kinds of things. It is a naturally occurring mathematical pattern that produces aesthetic scenes. Number theory is the branch of mathematics that deals with the properties and relationships of numbers, especially the positive integers. In number theory, there is a sequence known as the Pisano period, named after Leonardo Pisano. The period, written as pi of n, is the period with which the Fibonacci numbers taken modulo n repeats. The Fibonacci models can be applied in solid-state physics. This is the study of rigid matter or solids through methods such as quantum mechanics, crystallography, electromagnetism, and metallurgy. They can be used to enhance the descriptions of media known as quasicrystals, which is a structure that is ordered but not periodic. Last but not least, Fibonacci helped switch Europe over from the widely used Roman numerals to the Hindu-Arabic number system, which consists of the numbers 1 to 9 and most importantly 0. The system also included a place value system, or decimals, therefore allowing for more complicated mathematics.